Welcome to our deep dive into the fascinating world of the speed of light. For centuries, it tantalized thinkers and dreamers alike, a fundamental constant governing the universe we inhabit. Is it a wall, forever barring us from reaching unimaginable speeds, or is it a doorway, waiting to be unlocked to reveal the secrets of time and space? Our story begins not with equations and laboratories, but with a celestial dance, the moons of Jupiter. In the late 17th century, Danish astronomer Ole Romer noticed something peculiar about Io, Jupiter's innermost moon. As Io dipped behind Jupiter, its eclipses seemed to occur later than predicted, when Earth was farther from Jupiter. Conversely, the eclipses appeared to happen earlier when Earth was closer. This discrepancy, Romer realized, wasn't due to some strange lunar behavior but rather the varying distances light had to travel across space to reach us. He had made the first crude measurement of the speed of light. Over the next 2 centuries, scientists refined Romer's observations, pushing the boundaries of measurement. Michelson's ingenious interferometer used mirrors to split and recombine a beam of light, creating an interference pattern that shifted subtly, depending on the speed of light. Today, our methods of measuring the speed of light have become even more sophisticated. Lasers, with their incredibly pure and focused beams, have become indispensable tools. By bouncing laser light off mirrors placed precise distances apart and measuring the time of flight, we can determine the speed of light with astonishing accuracy. Atomic clocks, the most accurate timekeepers ever devised, are now used in conjunction with laser interferometers to push the limits of measurement even further. These experiments not only refine our understanding of the speed of light, but also test the very foundations of physics. The quest to measure the speed of light is a testament to human ingenuity and our insatiable desire to understand the universe. From observing the eclipses of Jovian moons to harnessing the precision of lasers and atomic clocks, we've come a long way in unraveling the secrets of this fundamental constant. While measuring the speed of light is a remarkable feat, it has revealed something even more profound. This speed isn't just a number, it's a cosmic speed limit. This revelation came from the mind of Albert Einstein and his groundbreaking theory of special relativity. Einstein showed that, as an object approaches the speed of light, its mass increases infinitely, requiring an infinite amount of energy to accelerate it further. Therefore, reaching the speed of light itself would require an impossible amount of energy, effectively making it an insurmountable barrier for objects with mass. Particle accelerators like the Large Hadron Collider propel subatomic particles to near-light speeds. As these particles approach the speed of light, their increasing mass makes further acceleration increasingly difficult, requiring ever greater amounts of energy, and reinforcing Einstein's predictions. Neutrinos, those ghostly particles that flood the universe, come tantalizingly close to the speed of light. These elusive particles interact very weakly with matter, allowing them to pass through us, through the Earth, even through stars with barely a whisper. Recent discoveries have shown that neutrinos do possess a tiny amount of mass, though it's minuscule even compared to other subatomic particles. This means they travel slightly slower than the speed of light, though the difference is incredibly small. Measuring the speed of neutrinos is a monumental challenge, requiring sophisticated detectors buried deep underground to shield them from cosmic rays. The concept of exceeding the speed of light is tantalizing, leading to some truly mind-bending theoretical possibilities. One such possibility is the existence of tachyons, hypothetical particles that always travel faster than light. Unlike ordinary matter, tachyons would actually gain speed as they lose energy, with the speed of light acting as a lower limit rather than an upper one. While the existence of tachyons hasn't been ruled out, there's currently no experimental evidence to support it. Their existence would raise some serious paradoxes, potentially violating the fundamental principle of causality, the idea that cause must always precede effect. Despite the lack of evidence, the concept of tachyons continues to intrigue physicists and fuel our imaginations. While the speed of light seems like an unbreakable speed limit for anything within the universe, there are phenomena that appear to defy this cosmic rule. One of the most intriguing is quantum entanglement, a bizarre connection between particles that allows them to communicate instantaneously regardless of the distance separating them. Imagine two particles linked in this way, separated by vast distances, even light-years. If you measure the state of one particle, the state of the other instantly changes to reflect that measurement, as if they somehow knew what happened to their entangled partner. This instantaneous connection, seemingly faster than light, has puzzled physicists for decades. But there's a crucial distinction to make. While entanglement allows for instantaneous correlations, it doesn't allow for the transmission of information faster than light. Then there's the expansion of the universe itself. The fabric of space-time itself is stretching, carrying galaxies away from each other at increasing speeds. Let's indulge our imaginations for a moment and imagine what would happen if we could exceed the speed of light. One of the most profound implications is time dilation, a consequence of Einstein's theory of relativity. As you approach the speed of light, time itself slows down relative to a stationary observer. This means that if you were on a spaceship traveling at near light speeds, time would pass more slowly for you than for someone back on Earth. If you could somehow exceed the speed of light, time might flow in reverse, allowing you to journey into the past. But traveling back in time raises all sorts of paradoxes. What would happen if you could go back and prevent your own birth, or alter a historical event? Another consequence of superluminal travel is the violation of causality. Why is the speed of light such an unyielding barrier? Einstein's equation, E equals mc squared, describes the relationship between mass and energy. Mass and energy are interchangeable. As an object approaches light speed, its kinetic energy increases dramatically. This increase in kinetic energy is equivalent to an increase in mass. The closer it gets to light speed, the more energy is required to accelerate it. This is why the speed of light acts as a cosmic speed limit. One of the most mind-bending consequences of special relativity is the idea that time is not absolute but is relative to the observer's frame of reference. This means that time can pass at different rates for observers who are moving relative to each other, a phenomenon known as time dilation. Imagine two clocks, one stationary and one moving at a constant speed. According to special relativity, the clock in motion will tick more slowly than the stationary clock. The faster the moving clock travels, the slower time passes for it relative to the stationary clock. This effect might seem counterintuitive, but it's been experimentally verified countless times. For example, atomic clocks flown on high-speed jets around the world have been shown to tick slightly slower than identical clocks on the ground, precisely as predicted by special relativity. Time dilation isn't just a theoretical curiosity, it has practical implications for technologies like GPS, which rely on incredibly precise timekeeping. If time slows down as you approach the speed of light, what happens when you actually reach it? Does time stop altogether? According to special relativity, as an object with mass approaches the speed of light, time slows down relative to a stationary observer. At the speed of light, time dilation reaches its extreme. Time essentially stops for the moving object relative to the outside universe. But there's a catch. No object with mass can ever actually reach the speed of light. As we've discussed, the mass of an object increases infinitely as it approaches the speed of light, requiring an infinite amount of energy to accelerate it further. For massless particles like photons, which always travel at the speed of light, the concept of time takes on a different meaning. From a photon's perspective, time doesn't pass at all. The idea of traveling faster than light has captured our imaginations for decades, fueling countless science fiction stories and inspiring generations of scientists and engineers. But is it truly possible, or is it destined to remain in the realm of fiction? Exceeding the speed of light seems highly unlikely within our current understanding of physics. However, theoretical possibilities like warp drives and wormholes could circumvent these limitations. Warp drives could distort spacetime to allow faster-than-light travel. Wormholes might connect distant points in spacetime, enabling instant travel. While speculative, these ideas continue to inspire scientific inquiry and push the boundaries of our understanding. Thanks for joining us on this journey through the cosmos as we explored the mysteries of light speed. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating content. The universe is full of wonders waiting to be discovered, and we're here to guide you through the latest scientific discoveries and explore the biggest questions about our place in the cosmos. stay curious, and keep exploring the wonders of the universe.